Hi, welcome to the Intermediate to Advanced Linux series from CBT Nuggets. In this series, we're going to expand on what we did in the Introductory Linux series. So you should have either worked through that material or be sufficiently experienced with Linux in some other way. Now, I'm still going to explain all of the material in this series in a comprehensive way. I'm just not going to walk you through all of the preliminaries for topics that we covered in the last series. In this series, we're focusing specifically on Red Hat Linux to help prepare you for the RHCE exam, the Red Hat Certified Engineer exam. This is currently the most comprehensive and practical Linux certification out there. And working through the material in this series, followed by hands-on practice, will help prepare you to be an RHCE and a competent system administrator. So there's no use sitting around, pull up a chair, and let's get started. Let's start by talking about some pre-installation considerations, and I've listed out three categories here: the business perspective, the user's perspective, and also technical issues. Now, the majority of our time in this video and the next video we're going to be spending talking about technical issues with regards to installation and pre-installation. But first, I just wanted to give you a little taste of the business perspective and the user's perspective first. If the system that we're talking about is your home system and nobody else uses it, well, you can do whatever you want with your Linux installation since the decisions aren't going to impact anyone else. But if you're in some small business or corporate environment, you're going to have to think about things from the business and the end user side of things. I've listed a couple questions here to get you started. Is the Linux system going to be the main system or some supplemental system? And by supplemental, I mean like a file server, or a mail server, something like that. And then are you starting fresh or are you migrating over some existing service? Now, if you're migrating over the main system at a small business, say, to Linux, well, you're bound to be met with a great deal of resistance from end users because people are just creatures of habit and they don't like to change the way they do their daily tasks. And from a business side of things, this might not make a lot of sense to migrate over the main system to Linux because if the end users aren't familiar with Linux, then their productivity is going to go down. Perhaps there's going to have to be some training costs and things like that. But whereas if you're migrating over, just say, the mail server for this small business, well, that might be a really good business decision because you're going to save on licensing fees. Maybe in your estimation the server is going to be more high performance, and so maybe you don't have to upgrade the hardware as often, those sorts of things. And from an end user side of things, they might never even know that you migrated over the mail server, right? If you did sufficient testing and the migration goes smoothly, the end user shouldn't be impacted at all. Now, if you're starting fresh, say you're the new tech guy at a brand new small business, and the end users are game to use Linux, well, then you might have a little bit more leeway here because the end users aren't ingrained in any habits yet, and they can form their habits on this Linux system. And Linux is getting so easy to use with all the graphical user interfaces. There's high schools that are using Linux to teach computing to people because of the licensing fees are so cheap. So end users are not having as big of a problem getting started with Linux as they were, say, 5 years ago or 7 years ago, or something like that. Okay, because of all the GUIs and everything, it's making the system so much easier to use. So that's just like a little taste of the business and the end user side of things. Now let's move on and talk about some technical issues with regards to installation. Well, the first thing we're going to talk about are hardware constraints, like how much hardware do you need to run Linux, how much main memory, how much disk space, what kinds of hardware can you hook up to Linux, what's compatible and what's not compatible, how many devices can you hook up to your system. Now, that number of devices you can hook up is somewhat related to interrupt request ports depending on what kinds of devices we're talking about. And we're going to talk about these IRQ ports and the other communications channels in a typical Linux system. We'll talk about how to identify which devices are hooked up to which ports and why that's important. And then we'll talk about disk space, how to partition the disks, and this we'll just give a partitioning introduction today. We'll talk about some terms, we'll talk about the basic ideas behind partitioning, why we want to partition, and then this will carry over to the next video where we'll actually talk about the tools that we use to partition, and we'll walk through some case examples of partitioning in different scenarios. Okay, so let's get started by talking about hardware constraints first. So how much RAM or main memory do you need to run Linux effectively? Well, it depends on a few issues. The first one is, are you running Linux at the command line, just a text-based interface? If that's all you want to do is run Linux in a text-based, with a text-based interface, all you need is 32 megabytes of main memory. Now, I've put a plus sign out here because adding more main memory than that will only increase the performance of your system. Okay, maybe just because you're running it at the command line doesn't mean you're not doing something that's intensive, right? Maybe you're running some intensive scientific calculations or something from the command line. Well, then having more than 32 megabytes of main memory will certainly increase the performance of that application. Now, if you're going to move on and talk about graphical mode, all the GUIs and X windows and all that sort of stuff, then you need, I think, at least 128 megabytes of RAM to run Linux effectively. I've seen different numbers published here. I've seen 64, 96, 256, saying that's the minimum for running Linux in graphical mode. You know, you can certainly run it in less than 128 if you feel like the graphics are sluggish, the system is sluggish, or the graphics are jittery or something like that. Then, you know, try increasing the amount of main memory and to make the problem go away. Okay. Now, for a server, how much memory do you need for that? Well, you know, that's really a big question mark. It really depends on how many people are going to log in to the server simultaneously and what applications are being offered on the server that they're using. Okay, so if this server is sitting out here and only like 2 people simultaneously ever log into it, you know, and the application that they're using is not very intensive, then maybe 256 megabytes is sufficient for that server. Okay, but if maybe the server is a database server and, you know, 20 people are going to log into this server simultaneously, then 256 megabytes of RAM would probably feel very, very insufficient. And you should probably increase that 4-fold or something like that, you know, for like this 20-person this server that's going to serve 20 people at a time, you know. Okay, so that's the kind of issue you have to think about with servers. How many people is it serving and what kinds of applications is it serving up? And then there's a question of how much main memory can you have in your system. What's the maximum amount of main memory that you can have? Well, it depends on which kernel you're running. If you're running the 2.2 kernel, we're talking about 4 gigabytes of RAM. And if we're running the 2.4 kernel, we're talking about 64 gigabytes of RAM. Okay, so I'm laughing just because it makes me feel a little bit old to say this, right? Some people feel old when their children graduate college or something. But I feel old when I say the 2.4 kernel can address 64 gigabytes of RAM, which is bigger than any hard disk that existed when I started out computing. Okay, so you know, this makes me feel a little old. But anyway, my problems aside, we'll talk about hard disk space. If we're talking about a server with no X windows, we're talking about 850 megabytes of hard disk space. For a basic workstation installation, there we're talking about all the GUIs, X Windows, Office software, basic stuff like that. We're talking around 2 gigabytes of disk space. And if you're talking about the full installation with you know, web servers and Emacs and you know, every piece of software on the Red Hat installation CDs, then we're talking around 5 gigabytes of space. And these are the numbers here for Red Hat 9. Okay, and if you're talking about an earlier version of Red Hat 8.0 or 7.2 or something back then these numbers are only smaller for the older versions of Red Hat. So these are the maximums for hard disk space that you'll need for the newest version of Red Hat that's out there. Okay, so this gives you a little taste of how much main memory and hard disk space you're going to need to run Linux effectively on your system. I just want to give you a quick little tour of where you can get hardware compatibility information for Red Hat Linux. And the most authoritative source of this is actually from redhat.com, and I've bookmarked it here, the Red Hat Hardware Compatibility List. So we're going to open this up in Mozilla, and you can see the address is actually hardware.redhat.com/HCL, which stands for Hardware Compatibility List. Okay, now under this list, there's some different subcategories. There's the Red Hat Linux 9 compatibility information. Okay, and then there's the hardware compatibility list. So if you're talking about Red Hat Linux 9, you need to click here. If you're talking about 8.0 or earlier, you need to click here. Let's click on this one first because it's got some information in there that I want to show you that's a little different than the stuff for Red Hat 9. Okay, so here we have, again, various classifications. We can look up by certified hardware, meaning we can look up which hardware has been certified by Red Hat, and it's passed the Red Hat Ready test, is what they say. Okay, now this hardware that's been certified Red Hat Ready means that if you buy the official Red Hat box set and you install Red Hat Linux on hardware that's been certified, then Red Hat will give you support, a good deal of support, because they believe that this hardware and software should work perfectly together. Okay, so again, this is certified hardware. If you need Red Hat Linux 9 hardware, you need to click here. Okay, so certified hardware, we're going to click on that, and what it does is it says choose a manufacturer, and you can see here all the various manufacturers that are out there. Okay, let's just pick Dell and see what they say about Dell. And then there's some subcategories: desktop, workstation, laptop, server, and so on. We'll just click workstation over here. And now it lists different Dell computers and the versions of Red Hat Linux that they've been certified to work on. So here, just take this one. The Precision 420 has been certified to work on Red Hat Linux 6.2. If you scroll down this list, you'll see newer versions of Linux over there on the right. If we go all the way down to the bottom, you'll see here's the Optiplex GX260. And that has been certified to work on Red Hat Linux 8.0. Okay, so if you're running this version, if you're installing this version of Linux on the corresponding machine that's over here on the left, then Red Hat supports that setup, and they will give you support if you're having problems installing or running this version of Linux on the various machines on the left. Okay, now let's go back a couple levels and look at, instead of just looking at certified hardware, let's look at the complete listings of all hardware listings for Red Hat Linux. Okay, again, it's going to give us a list to choose from, but now this list is way longer. Okay, because this is all the hardware for Red Hat Linux, not just the hardware that's been certified and guaranteed to work. Okay, let's just pick one in here. Let's pick NVIDIA. I have an NVIDIA graphics card, so we can see what that says about. Okay, so here it says, please select the hardware category for NVIDIA. There's only one choice, the video device controller. So I'll pick that. And now, again, it's going to list various different NVIDIA graphics cards and different versions of Linux, and saying whether they work on that version of Linux. Okay, so there's different grades here. There's this green check mark and there's this yellow question mark. And then on the last screen, when we were talking about Dell workstations, the little picture here was the guy in the red hat, and it was said it was not just compatible, it said it was certified or Red Hat ready. Okay, and so the compatible means Red Hat's looked at it, but they're not guaranteeing that it'll work. They'll still offer support for it, but they haven't put it through those rigorous tests to say that it's Red Hat ready. So you can see here it says NVIDIA Various. So if you click on Various, it'll tell you which actual video cards it's talking about. It's talking about, you know, all these video cards, the GeForce, GeForce DDR, GeForce 2, and so on. Okay, and then it's saying where's the driver location. Well, it's on the installation CD, so you shouldn't have any problems there. If you pick this video card during installation, it'll have the driver for you. And then the ease of installation out here is the little pointer is on green all the way out to the right, which means it's really, really easy. Okay, so this is like 5 grades: 0, 1, 2, 3, and 4. Okay, and each of those grades, as it goes to the right, gets easier and easier to install. If it's all the way over here on the left, that means it's really hard to install. You're going to have to, modify source code or something to get it to work. Okay, so again, let's back up and look at more NVIDIA graphics cards. Again, as you scroll down this list, you'll see newer versions of Red Hat Linux down here. Here's Red Hat Linux 8, and the GeForce 2 MX has been deemed compatible to work with Red Hat Linux 8. Okay, now if you scroll back up, let's just look at this one that's a yellow question mark. This is the GeForce 2 MX, and it's for Red Hat Linux 7. Red Hat has not said that this is compatible with Red Hat Linux 7, but somebody out there in the Red Hat Linux community has supplied some information. Positive, maybe negative. Click on the yellow question mark if this is your setup, GeForce 2 MX and Red Hat Linux 7, and you can see the experience that other people have had. Okay, again, all these different classifications are explained up here under the hardware status legend. If we click on that, you'll see what all these different grades really mean. So the top grade here is the little guy with the red hat. That's certified or Red Hat ready. Okay, they will support those setups, the hardware and software that are recommended under there. They will give full support to that. If it's got an X next to the hardware in some list, that means it's not supported. You should stay away from that hardware. If it's got a green check mark, that means it's compatible. It means they've tried it. It basically works, but they haven't put it through the rigorous test they put the certified hardware through. And then, of course, there's the community knowledge, and you need to take that for what it's worth. It's not the knowledge that's been put out there by the community has not been verified by Red Hat or anything like that. So you have to take this information that's out there under the community knowledge and make your own best judgment about whether it's good or not. Okay, so like I said, these are the different levels of classifications for the hardware. And remember, if you're looking at Red Hat 9 hardware, we're going back here to the original screen, and under those, for Red Hat 9 hardware, you need to look under this link to determine Red Hat 9 hardware compatibility. And you can actually see the first line here says Red Hat will actually not be certifying brands or models of hardware for Red Hat Linux 9. So if you want certified hardware that's Red Hat ready, you need to look at Red Hat Linux 8.0 and earlier to get that highest level of certification from Red Hat. Okay, so there's a quick little tour of how to determine hardware compatibility for your system. Now I want to move on and talk about Intel communications channels. And when I say Intel, I mean anything that's Intel compatible, like AMD, for instance. There's 3 communications channels used in the Intel architecture. There's the interrupt request ports, or the IRQ ports. There's input-output, or I/O addresses. And there's DMA, or direct memory access channels. Okay, these are the 3 communications channels that are common to all computers in the Intel architecture. And I just want to explain the differences between these and kind of give you a feel for how they work. And then we'll go on and talk in more detail about IRQ ports, because they're probably the most important to understand from a system administration standpoint. Okay, so central to this whole thing is the CPU, the central processing unit of your computer. And the CPU in an Intel architecture is interrupt driven, meaning that when some device external to the CPU, like a keyboard, wants to give information to the CPU, it generates an interrupt. And just like what it sounds, it interrupts the CPU. It says, hey, CPU, stop what you're doing and take this information that I'm trying to give you. Maybe the central processing unit is running a program that you executed, and on the keyboard you're hitting Control-C to abort that program. Okay, so when you hit Control-C on the keyboard, that generates an interrupt. The CPU looks at the interrupt, says Control-C, and then it aborts the process that was in the foreground when it received the Control-C. Okay, so that's basically how an interrupt works. Maybe the best way to explain it is what the alternative to an interrupt is, and that would be polling. Instead of the keyboard generating an interrupt and telling the CPU that it has something for it, the CPU could poll the keyboard every millisecond and say, keyboard, do you have anything for me? No, okay, I'm going to go on and do what I have to do. Hey, keyboard, do you have anything for me? No, okay, I'm going to go back and doing what I was doing. So polling requires the CPU to do all the work, which is bad because you want the CPU to be doing other stuff like running your programs, okay? And if the CPU has to poll all the various devices that are out here, a lot of its time is going to be bogged down polling, and that's why they went with this interrupt model where the devices interrupt the CPU to request a service, okay? So that's how interrupt request ports work, basically. All right, let's talk about input-output addresses. Say you've got a hard disk out here, okay, and down here is your memory. This is RAM. And then over here is a printer. Okay, that's my printer there. Okay, nice printer. All right, so you can see I didn't get a degree in art. Okay, so the input-output addresses, what these are used for is so that, say there's a file on a disk, and you want that file to be printed out. Okay. Now, instead of the file on disk going to the CPU and then the CPU going out to the printer to give that information to the printer, well, what's the slow link in this chain? Disk, CPU, printer. What's the slow link? Well, it's the printer. Okay. And so if we went from the disk to the CPU to the printer, disk, CPU, printer, the bottleneck is going to be the printer, and that's going to bog down the CPU for some inordinate amount of time. So alternatively, what they've done is they've used input-output addresses to ease that. So what happens is the disk, again, generates an interrupt request to give information to the CPU, and the CPU writes it out to memory. Well, there's this portion of memory out here that is reserved for input-output. So these are the input-output addresses in this special part of memory over here. Okay, so the information comes to the CPU writes it out to the input-output addresses. The disk transfers this, and everything goes to this input-output address. When this is done, the CPU is now free to go off and do something else, and the device, the printer device, now takes this information out of this particular area of memory and then prints it out. It knows where this is because each device that's out there, like a serial port 1, has a specific spot in memory where it's going to go and read this information from. Okay, so the device driver here says, hey, there's something out there in memory for the printer to print. The printer goes and takes care of it on itself. Meanwhile, the CPU is left free to do whatever it's got to do. Okay, and the last one here is a direct memory access channel. So this is another kind of way that devices communicate in an Intel system. Now for this one, let's talk about a sound card out here. Okay, so here's my sound card, and over here are my speakers. Okay, so if I have some file on disk, some song that I want to play, then what I can do is, because my sound card has its own little processor, the sound card can set up a direct memory access channel and bypass the CPU altogether. Okay, so the disk can transfer to the sound card, and the sound cards can then play it out of my speakers, and the CPU's out of the loop. So that's good, because then the CPU is left to free to do whatever it's got to do otherwise, and the sound card can take care of the processing required to translate, that MP3 or whatever file is on your disk into the format that the speakers can understand. Okay, so that's what the sound card does, and it takes care of all that processing and leaves the CPU free to do other stuff. Okay, so there's a very basic overview of how communications channels work in the Intel architecture. Now let's move back out to the Linux screen and talk a little bit more about interrupt request ports, and so you can see which devices are assigned to which ones. So let's look at the IRQs that are already in use on this system, and the way that we can do that is we go to the proc/interrupts file and we print that out to the screen. Okay, so there are 16 IRQ numbers ranging from 0 to 15. All right, and you can see here by just looking down this list that not all of them are in use. First, let's talk about the ones on my system that are in use, what they interpret to, and then we'll talk about the ones that are free, and typically where devices get assigned to IRQs, and then we'll talk about what to do if you are run out of them and you try to add some device. Okay, so here the system timer is IRQ0. This is a standard assignment and you can't change that. IRQ1 is typically the keyboard. IRQ2 is listed here as a cascade. That's just for backwards compatibility to old systems. There used to be 8 IRQs, and then they would add on an additional 8, and you'd communicate with the second 8 through port 2. Okay, so that's what the cascade means, but we don't have to know too much about that. RTC is a real-time clock. This is a USB hub, a network card, SCSI adapter, a PS2 mouse, and an IDE hard drive. Okay, so let's talk about the numbers that are missing here. 3 and 4 are 2 IRQs used for serial ports. Number 5, IRQ5 is used for a parallel port or a sound card or something like that. Channel 6 is a floppy disk controller. Channel 7 is another parallel port. Let's see. And then 13, 14, and 15. 13 is for a math coprocessor. If you have that on your chip, that's where IRQ 13 is used for. And 14 is for another IDE drive. Okay, so that's sort of the basic assignment of the devices to IRQ numbers. Now, if you're adding a device to the system, typically the system will assign the IRQ itself. Okay, so if you plugged in a parallel device to the system, it would take over on port 7 or port 5, depending on how it's configured. You can set it up for serial devices, like for serial ports 3 and 4. You can use the set serial command, which we talked about in the introductory series. You can use the set serial command to actually add a device and give it a particular IRQ number. Maybe if we do a man on set serial to refresh your memory a little bit, you can give a device and these parameters, and if you go down this list here, you can see one of the parameters is IRQ, and you give it an IRQ number. Okay, and so you can set up the device to have a particular IRQ. What you want to make sure, though, first is that you make sure that you're not conflicting with an IRQ that's already in use, because if 2 interrupts can come on the same channel, then your system can hang, because the CPU doesn't know which device is hooked up to that channel that it needs to service. Okay, so that would be a problem if you assign 2 devices to the same IRQ, and to double check, just look at the proc interrupts file to make sure you're not doing that. So are you running out of IRQs and you need some more devices on your system? Well, usually this isn't a problem because the kinds of devices that you're going to add to your system are probably either PCI devices or USB devices. Now, PCI device, if you have a PCI slot open in your motherboard, you can plug a device in there and it can share the same IRQ as all the other PCI devices. And this is because the PCI bus manages the way that each PCI device shares the IRQs. So there's like, the PCI bus is like a higher level manager to these IRQs for the PCI devices. Same goes for the Universal Serial Bus Controller. The USB controller governs the way USB devices and how they share IRQs. Okay, so again, these two devices, if you're adding one of these two kinds of devices to your system, it's not a problem if you're running out of IRQs because the individual controllers will take care of how they manage the IRQs. Now, if for some reason you need to add like 10 serial devices to your system, you're going to run into problems because there just aren't enough IRQs to do that. So see if you can convert or find similar devices that either use the PCI or the USB interface, and then then you can use those devices in that interface instead of the regular old serial interface. Okay, if all else fails, I guess you'll have to go to Device Addicts Anonymous because you have too many devices on your system. Okay, so for me, this has never been an issue. I've never run out of IRQs on a personal computer of mine. I'm not the kind of person that hooks up like 97 different things to my computer, but if you are that kind of person, then look into USB and PCI devices because that's going to make your life easier. You're not going to run out of IRQs in those instances. All right, so now let's move on and talk about disk partitioning for a little while. We should already have an idea of what a partition of the disk is. It's when we take our hard disk and we chop it up into various sized chunks. Okay, why do we want to do this though, you might be asking yourself. Well, one of the reasons we want to do this is that we can keep applications and system files and user files all in separate partitions. One of the reasons we want to do that is so that we can protect against runaway programs. So say over here there's a user's program that they've written and the program's malfunctioning and the program writes to a file but it's malfunctioning, so the file just keeps getting bigger and bigger and bigger. The program doesn't ever stop. Okay, well what's going to happen is this program is going to end up writing to this file and the file is going to grow so big that it's going to fill up the entire user partition. Okay, now when it does that, it's not going to be able to make the file any bigger because the user doesn't have permission to write to these other partitions that are out here. And that's good because critical system stuff has to be able to write to log files and take care of things like that, and this runaway user program is not going to affect the critical operation of the system. Okay, another reason we like to partition is that the recovery time from corruption is reduced. So say some small part of the disk becomes corrupt right there. Well, what we have to do then is we only have to restore this partition, and the other 3 partitions we can leave alone. Okay, so by restoring just a smaller part of the disk, the recovery time is reduced. Another reason we like to partition is for improved security. If this is the applications partition here, well, we can make that partition read-only. Okay, there's no reason that anybody, including system programs, need to write to the applications partition, and so by making it read-only, we're adding an extra level of security to our system, so we know the applications aren't going to be tampered with. One of the things you want to be careful of, though, is over-partitioning. We don't want to end up chopping our disk up into 100 little tiny partitions, because what's going to end up happening is that it's too fine-grained of a division, and you're going to find out that a partition's going to fill up over here, and there's going to be lots of unused disk space in these other partitions, but we can't make this partition grow any larger. Repartitioning on the fly it's just not possible. Okay, so what we have to do is we have to add a new disk now to our system to have this partition sort of grow onto that other disk. Okay, so we don't want to chop it up so fine-grained that we wind up with lots of wasted disk space, but we want to have at least a few partitions so that we can keep the major parts of the system separate. Now let's move on and talk about some of the gory details relating to partitions. Alright, so let's talk about some definitions first. The first definition is a primary partition. Okay, what is a primary partition? Well, on your hard disk, there's what's called a partition table, and this partition table can keep track of 4 partitions, and those 4 partitions it keeps track of are what's called the primary partitions. Now, that doesn't mean that we're limited to 4 partitions on our disk. We can have more than 4 if we make one of these primary partitions what's called an extended partition. Now, this extended partition is a kind of primary partition, but what's different about it is that an extended partition can contain many what are called logical partitions. So there's our 3 definitions: primary, extended, and logical. Okay, so the way this would work is something like this. We would make, if we wanted more than 4 partitions on our system, we would make 3 primary partitions labeled here with P's. Then we would make 1 extended partition, this whole big chunk, and we would chop those extended partitions up into little logical partitions. Okay, so now we've got 6 partitions on our system, 3 primaries, 1 extended, and that extended contains 3 logical partitions. Now, the number of logical partitions that an extended partition can contain depends on what kind of disk we have. If we have an IDE hard disk, then we can that extended partition can contain 60 logical partitions. If we have a SCSI disk, that extended partition can contain 12 logical partitions. So let me just review something from the introductory series, just to make sure you remember. The labeling for IDE and SCSI disks is pretty standard in Linux. So IDE disks start with HD, and SCSI disks start with SD. Okay, this is true in every Linux system. The first IDE hard disk has a label A on the end of that. HDA is the first one, HDB is the second IDE disk, HDC is the third one, and SCSI disks are similar. SDA, BC are the first, second, and third disks respectively. After the first 3 letters, there's a number representing the partition number. So HDA1 would be the first partition on the first IDE disk. HDA2 would be the second partition on the first IDE disk. Okay, again, the same for SCSI disks. So up here, the numbering for this scheme would be this one would be 1, say this one's 2, this one's partition 3. The extended partition would be partition 4, and then the logical partitions inside would be 5, 6, and 7. Okay, now partition 4, you can't really write data to partition 4. Partition 4 is this extended partition that just keeps track of these logical partitions inside of it. So you could never write data to like HDA4, for instance, in this example, because HDA4 isn't really a partition. It's just an extended partition that holds these logical partitions. Okay, and here's another thing to note, is that logical partitions will always, the first logical partition will always be numbered 5. Now that seems to make perfect sense, right? 3 primary partitions, the extended partition is 4, and so sure, the first logical partition is number 5. However, it's always going to be labeled 5, even in this scenario over here. Okay, so say I do this. Say I make a primary partition, I make another primary partition, and then say I make the rest an extended partition, and I stick 4 partitions in there. So this disk has 6 partitions, just like this disk has 6 partitions. Okay, now over here though, the numbering is going to be like this: 1, 2, 3 for the extended partition, and then 5, 6, 7, 8. So there's no partition 4. And there's no real problem with that. Some people do find that a little bit confusing, but this can lead to problems later, so don't do this. If you need more than 4 partitions on your system, follow this scheme over here of where you label it 3 primary partitions, 1 extended partition, then however many logical partitions you need inside of that. And remember, the number of logical partitions you can stick inside there depends on what kind of disk you have. If you have an IDE disk, you can have a total of 63 partitions on your disk, and for SCSI disks, we have a total of 15 total partitions, and here I've listed out the labels for the logical partitions on each of these disks. Alright, well, it's time to wrap up our first video. We talked about hardware requirements, like how much RAM and disk space we need to run Linux. We talked about hardware compatibility and how to use the Red Hat hardware compatibility list on the website. We talked about communications channels and IRQ ports and direct memory access and that sort of stuff. And then we started our discussion of disk partitions, and this is going to continue on into the next video. In that video, we'll talk about the tools that we use to partition disks, and we'll walk through a couple case examples of what a good partitioning scheme might be. Alright, well, I hope you found this nugget informative, and thanks for viewing.